Alright, time for another draftphysics.com video presentation. Anyway, comments. So this will mostly just be about the 1.4 thing. I guess it's the square root thing. It's the somehow momentum isn't conserved in at least springs thing. So I don't know how to exactly address it, but we'll go through some of their, mathematics. I don't know. I don't even know if it qualifies as mathematics, frankly. But anyway, as if meaningful, saying anything. So the problem is I would just argue that it's kind of known just because you can bounce something back and forth between two springs, that what springs actually do is they conserve the motion, the stuff that causes the motion. So if I'm bouncing a ball between two equal springs, it'll keep going back and forth for quite a while, before friction. And the more friction I can eliminate, like on an air track, it'll do this for, minutes. And just a fact. So springs are pretty good. They store whatever this stuff is. Now, I think it's perfectly sensible to call this stuff motion momentum. Okay, P, whatever. Mass times velocity. Works perfectly fine, perfectly sensible. It's sort of how Newton saw the world. There's just a volume of energy, and it's a volume. It's just a volume in a vessel, or like a fluid. You have a certain amount of it. Even the idea of joules, it sounds like an amount of something. Weight is an amount of something. And so you're basically just saying, I threw the amount into the spring gave me the same amount back. It didn't keep any of it. It didn't throw it away somewhere. It took it and gave it back. And then it takes it and gives it back. So, this idea that there's some special kind of energy the spring is storing, well, it's clearly giving back momentum. So momentum goes in and momentum comes back out. You want to say kinetic energy goes in and kinetic energy comes back out? It's okay to say it. The only problem is what you can't say is that the same momentum is the same thing as this. Okay, mv squared, 1/2 mv squared, the original one was mv squared, is not mv. So you can't say this volume is the same as this volume. Okay, they're not the same volumes. Okay, they're very different volumes. So, just rationally, it has to be conceded. You can't say they're compatible or they're saying the same thing or any of that crap. So the 1.4 thing comes up because they basically say, their theory is, I can compress the spring with a light object, the same amount that should give me the same stuff back. I mean, whatever I compress it, I put a volume into it, an amount, and it should give me, depending on what the compression is, the same amount back. It shouldn't make any difference. But they're saying it does make a difference, because if I put a heavy thing on there, same spring compression, I won't get the same amount out. It'll fail to function, in the sense that it'll give me more momentum or less kinetic. Yeah, if it gives me back kinetic energy, well, let's just see if we can just say it correct. I guess I should have done the heavy object in, okay, and then I get less out from the, so that'll be the way we'll do it, right? Yeah, because that's what they're arguing. So I put a heavy object in, okay, with a mass and velocity, and a volume, and the volume of energy goes in, and then when I put a lighter thing on here, I don't get the same volume out. So somehow I went in with this volume, but now I'm only going to get 1.4 the volume back out. Yeah. This is 1/2 the mass. It's much smaller than 1/2, just for illustrative purposes. Okay, so only 1.4 of the volume of energy is going to be in this object. Now, like I said, I could reverse this and just hit with fast things and I get more energy out. Somehow the spring gives me back more than went in. So I create free energy. That's the paradox. So the argument, it doesn't make much sense. I would argue to anybody rational, 0.4 is not very much, right? We're talking about 0.4 out of 10. Okay, so we have the mass, we made it twice as light, and we only got 0.4 an increase in its speed. So it's like let's apply it to, say, race cars. So just imagine you're a race car designer, and you're sitting here with this, inane circumstance where they're basically saying to you, you can cut your car's, mass in half. Take out half the mass of the car, make it, weigh half as much, and you're only going to gain 0.4 in your velocity. So you're only going to go from like 30 miles an hour to whatever, 40 something. I don't know what 0.4, 60 would be what you're looking for. So yeah, you get 45, let's say. Since it's 1/3, it has to be less than that. So it's just like 40, right? Yeah. So instead of 60, which you were hoping for, you're only going to get 40. That really sucks. So, that's a pretty big hit you're taking for all of the trouble of reducing the car's weight by 1/2. So I don't think that intuitively makes sense in people's real world experience. Is that their real world experience, that's how it works? I don't think it is. So the point is we have no evidence except for Stephen Bro's experiment now. Okay, let's just count that. Okay, it's evidence. I'm saying it's pretty bad evidence, but it's evidence. And beyond that, what do we have? Nothing. Nothing validating this event that that I put the light thing in, okay, and I gain more momentum from the heavy thing out. So I just keep replacing light things with heavy things, and I'll just keep increasing and increasing and increasing the momentums. The mass times the velocity. I have to be increasing the velocity, obviously. So I'm just gaining a constant increase in the velocity ratio, however you want to look at it. The amount of velocity has to be spread on the bread. The amount of jelly. I mean, the velocity is the jelly, the bread is the mass. And they're basically just saying, here's a free jelly equation. Okay, but you only need a little bit of energy on a small thing, and you'll get a lot of jelly if you put it on a big thing. And if I just keep doing the same thing, I just keep, I take this big thing and crash it into a spring, and then replace it with a bigger thing, I got even more jelly. I can just keep increasing the jelly, the velocity, as a percentage of the bread. It's probably a good enough way to say at that beginning. So we have no experiments, and there's no real explanation of how it physically could be possible, okay, that you can do either one of these things: conserve kinetic energy and destroy momentum, or conserve momentum and destroy whatever kinetic energy is. That the two theories are not at all compatible, because it's a real destruction. It's not like the spring got hotter. There's no evidence that the spring did anything different when the heavy object was on it than the light object. No evidence to believe that it loses energy, because obviously I could bounce heavy things back and forth all day long and they still go back and forth with the same energy. So obviously the spring doesn't care. It works just as well. It's not losing energy by compressing and expanding. And its compression is just a distance. It compresses. You can't say it matters how it got compressed. Whether I push the spring in very fast or I push the spring in very slow can't make any difference. I mean, you got to know that logically. So how can this be even an argument? There's no compatibility here. These two theories can't live, side by side, and everything's just hunky-dory. That's nonsense. All right. So to the comment. So this is the JPG guy. Okay. So I asked Piro 2 questions you asked in this video. So the video is titled, I don't need no stinking evidence, right? DraftScience versus I don't need no stinking evidence. Because that's what your people are saying. You don't need anything to support your theories. You can just say it, and that's all you need. You don't need to show me anything. Okay? So it's in that context. That's what the video's titled. Okay, the questions. Let's say we already established mathematically that if you want to conserve kinetic energy, you use the 1.4 thing. Okay, so all right, we'll go further before we talk about the 1.4 thing, because the 1.4 thing only works when the ratio is 1/2, or more importantly, 2/1. So each time you double or triple or quadruple the differences in the masses, you'll change the whole number that you'll end up as a ratio. So if I put 10/5, that's 2. If I put 40 over 20, that's 2. If I put 60 over 30, that reduces to 2. So that's the only relevance the 2 has. It's just a reference to the ratio of the masses to each other, and that's it. So it's just a ratio, the square root of a ratio. That's why it's significant. So it only works, if I make it 61, mass versus 30, I got a new ratio, I got a new number. It's now 2.1, or 1.9. Okay, it's not the square root of 2 anymore. All right, I think that's a good enough brief way to say it. All right, use the 1.4 thing. So this is conserving kinetic energy. So you have to degrade the velocity of the lighter thing by essentially more than half of what you would expect the gain to be. Here's how much you would expect your gain in velocity to be when you cut something, you make the weight half as much. You expect the gain to be this much, and their argument is you only get this much. That's how bad it is. Okay, you get less than half of the expected gain. All right. But is there an experiment or demonstration actually showing that working? So there isn't anything else except Stephen Bro's experiment, Brough, right? So that's all we have. So in 300 years of them playing with this theory, that's the only experiment we have showing it. Okay, that's where we are. Or a paper or video that explains why that makes sense. So can we find any clip of a professor talking about it? That you should expect storage devices to be incapable of delivering any more than, in the case of halved mass to velocity ratios, the square root of 2, an extra amount of energy, or 0.4. That you'll lose 0.6 of the energy you should have gained. Okay, so has anybody talked about it, said anything about it, mentioned it anywhere? Is there a Veritasium video on the subject? No, nothing. And yet I'm sitting here having to argue it, right? So I have to argue their phantom theories. It's not even a conventional science theory. So the whole channel is based on arguing with conventional physics about how it's full of crap. And here I am being obligated to defend conventional physics against their theory, whatever it is. The unarticulated, that's the way it happens theory. Yeah, I think you could describe this as ludicrous, right? Okay, anyway. And a final question. So he does ask for an experiment or a demonstration with a question mark, and obviously they don't address that. Okay, so a final question. Is there in fact a theory that says it's okay to destroy conservation of momentum, which they're clearly arguing happens? The momentum is not conserved in the spring. The spring, as far as we know, conserves momentum when objects bounce back and forth between springs. So they obviously do conserve it. They don't lose it. They don't waste it. They don't squander it. So where did it go? Okay. Is there a real experiment showing Newton's third law being violated? So they don't pay any attention to that one either. All right, so Piro's answer. Oh my God! Starts with that. There is no 1.4 thing. Well, there sort of is in the most common case of inverse to mass to velocity ratios, which would be the half case. Everything happens, there's probably more cases where they do the half case than they do the third case, or they do the sixth case, or the 1/8 case. The 1/2 case is the very popular case. But anyway, so it sort of is a thing. It's a square root thing. So again, no, it's a ratio thing. The only way it works is if you reduce any real number into a ratio. So you're reducing 60 to 30 into 2/1, a ratio, to make it into a 2. So it's just about a ratio. All right, the number is appearing because we are talking about one mass being 2 times the mass of the other. Right, and so if it was 3 times, then it's the square root of 3. But it's only the square root of 3 for the perfect case of exactly 1/3. You know, 1/3 plus one tiny little bit of velocity, and all of a sudden we'd have the square root of some other number. Thus, square root of 2. So there's no real thus there, right? It's only the square root of 2 because the ratio of the masses to each other, 60-40, is 2. So if the ratio isn't 2, it's not going to be the square root of 2. Yeah, that's it. That's the bizarre thread they're hanging this on. Okay, if the one if the one base has 3 times as big, I don't know what that even means, then the smaller object's velocity will be square root of 3. So he's just saying if one mass is 3 times, so if it's 90 over 30, okay, in terms of the mass ratio, then that reduces to 1/3. I mean 3/1, or 3. And so what he's doing, he posts a link to an actual, just the Google calculation of the square root of 3. Like, we need to see the number for the square root of 3. So it's not a link to an experiment. It's not a link to a paper. It's not a link to a drawing. It's not a link to some explanation of how kinetic energy works. No, just a link of a calculator. Cool. No, not useful. All right, it makes sense. It really doesn't, because you can solve E equals 1/2 mv squared for V, and it's the square root of 2E. So the E would be what the 1/2 mv squared equals. So you take that number and double it, okay, and then divide it by the mass, and that'll tell you the ratio. So you'll end up with 90 over 30. So the square root of 90 over 30, let's say in the case of a 3 times. So in the case we're looking at, it's 60/30. So you end up with the square root of 60 over 30, which obviously would reduce to 2/1. 2. Right? So that's the gimmick. It's not, this isn't even clever. This doesn't even mean anything. Okay, so the inverted mass velocity thing works like that because the mass ratios and the velocity ratios. Well, clearly it's only the velocity ratios that, you could use either one, but they're obviously going to be inverted. So you'd end up with 1/3 instead of 3/1. So you'd have to invert the inversion. Anyway, the mass ratio is not the same as the velocity ratio because of the KE equation has 2 squared in it. So again, just the mass ratio is not the same as the velocity ratio. Yeah, it is. The ratio is exactly the same. That's the whole point of the inversion. So it is exactly the same. It's just the opposite fraction. If one is 90 over 30, the other one is, if one is 60 over 30, the other one is 30 over 60. So you can just use the same principle, you just invert the fraction. All right, the conservation of momentum is not violated. So of course it is. It's overtly violated. It catastrophically violated. You can't be understood any other way. The momentum's working when the ball's bouncing back and forth. Why does it stop working just because I change the mass of the ball? All of a sudden I lose momentum or I gain momentum? How did I do that? Just by changing the size of the ball? It doesn't make any sense. Same springs are pushing it. How can I possibly lose momentum? All right, mainstream physics says it's not violated. It doesn't say that. It says clearly in the experimental results that the thing moves twice as fast. That's what Professor Lewin overtly says in the video I'm reading a comment on. So I showed the Professor Lewin again. I showed that he's talking about conservation of momentum, and he's saying overtly, if you half the mass, you have to double the velocity. Not 1.4, you have to double it. So what can I possibly say? All right, to all these trolls and everything else, I am somehow being unfair and unreasonable because I'm saying, you're saying mainstream physics says something. Well, can you show me them saying it? Because I can't find Professor Lewin saying it. Who says it? What professor says it? Every single professor I heard says you have to conserve momentum. So what sense does this make? Can you understand, trolls, that this is just noise now? This is just such nonsense? You have no conventional theory to argue from, and yet you're telling me conventional physics has proved it. Where do they do that? And where do they even argue it? All right. I mean, yeah, so is there a fair cop in the audience somewhere who'll just point out that, yeah, this is too insipid? Here I am attacking conventional physics, and I'm put in the ludicrous position of having to defend a conventional theory against people who are saying they're defending conventional physics, and I'm having to defend conventional physics against their description of conventional physics, which obviously isn't conventional physics. All right, that's where you heard of the idea. I didn't hear of the idea, so that's just crap. But don't bother trying to understand what that means if you don't understand it applies to elastic nature of collisions. So that's really not their nature. Their nature is to be kind of inelastic, actually. And as Professor Lewin says, you have to work hard to make them very elastic. That's why you put springs on them, is to force the hard things to be more elastic. You get it? There's just there's just no point. If you people are going to allow somebody to say this crap that's just so way off the subject and just so inaccurate in terms of describing what the actual conventional physics is saying, and keep applauding that these are good arguments, I mean, come on, this is pathetic. The conservation of momentum and kinetic energy work perfectly together. I mean, how can anybody say this when they obviously never work perfectly together? Ever. I mean, ever. I mean, only in the case of when you have two identical masses. So only in the case where you have identical mass and velocity objects do the numbers for kinetic energy and momentum match. I mean, in terms of at least there's not a conflict. They won't be the same numbers, but at least there won't be a there won't be a conservation problem. But in every other case, there's a conservation problem. Any change to the mass, and you have a conservation problem. Any change. So, I mean, is this a sensible statement to be made in 2021? The conservation of momentum and kinetic energy work perfectly together, when there's absolutely zero evidence that they ever work, ever. In every case where you'll see a difference in kinetic energy and momentum, they're not working together. Like I said, even in the perfect case, they're not working together. I almost want to take that back, just because you could get the same joule number if you just do the multiplication of the momentum number times the 2.3. But anyway, let's just play along. I mean, that's the case, you know, right? So if we just take the case of the and presume you have two objects that's exactly the same, moving away from us, the same force, you know, a common force. So they have to leave at the same velocities and mass ratios. But when you calculate the kinetic energy, it's obviously going to be a big number versus the momentum number because nothing's squared. And if I multiply the momentum number, I'll have to see if that works. If I multiply the momentum number times a constant, like 2.3, will I get the kinetic energy number? Will it match the number of the velocity squared? So in that one case, it might be true. But I'm just saying in every other case, the two numbers are overtly inconsistent. Momentum says it takes the same energy to move the dime 1,000 miles an hour as it takes to move 2 kilograms 1 mile an hour. Kinetic energy says it took 2,000 joules to do one thing and 4 to do the other. How is that working perfectly together? All right, anyway. KE is F times distance. So the whole force times distance thing has absolutely nothing to do with this because this isn't gravity. This isn't a constant force. Springs don't even release their energy probably in any constant way. They release it based on how much tension they're under. So they're at high pressure, and as they start expanding, the pressure reduces. So the amount of energy they're adding to something's velocity would be less and less as the spring expands more and more, logically. So it can't even be, it shouldn't even be described in this way. And so there's lots of physicists who will point that out, that these rules only apply in circumstances where there's a constant force. It doesn't have anything to do with impulse. It doesn't have anything to do with collisions. But they don't care about that either. You know. So they just say this crap. KE is force times distance, and momentum is force times time. What is that telling you? Time and distance have to be related to each other perfectly to get a velocity. Velocity is the same distance and force. You can't change the distance and time and have the same velocity number. So clearly that doesn't make any sense. All right. So anyway, this guy, without being asked to answer the question, is sort of answering the same question. I don't need reply. I need more. There it is. Oh, I don't remember being this long. But anyway, so we'll give him his shot. I thought it was very Puro-esque. I mean, it's just the same jargon about mathematics. But anyway, let's go through it. No 1/2 mv squared falls out of mathematics when we want F equals ma. So again, we're back to this. That isn't Newton's formula, okay? Newton said force equals change in momentum over the change of time. And the change in time was just there to give you units. So the force would be in per second, per minute, per hour units. If you just get rid of the time, then it's just total momentum. And so what you're saying is the force equals the total change in the total momentum. And so force equals momentum. Simple. Now, you won't tell me why that derivation isn't perfectly simple, perfectly accurate. Okay, F equals ma be equal to momentum. When we want F equals ma to be equal to momentum, which doesn't even mean anything, right? Because Newton's original formula was momentum. So it already equaled momentum. So what sense does that make? They say F equals ma is the same thing as F equals change in momentum over change in time. They say those two things are the same thing. Why would I have to make it equal momentum? Why would I have to do that? Anyway, the first measures momentum and the second one measures force. So again, what Newton is overtly saying is the exact amount of the change in your momentum will be exactly what the force was. That force equals momentum. He's pretty clearly saying it. I mean, there's no way to get around it unless you think the time thing does anything other than create units. Per second, per minute, per hour. Just tells you how much force there is per unit of time. But if you don't care about units of time, you just care about the total force, then F equals mv. Talk your way out of that. Explain why that derivation isn't legitimate. Yeah. All right. Anyway, the first measures momentum, the second measures force, and we want the answer to be the same. Again, and you couldn't get any clearer. Newton already said they're the same. So when we do that mathematically, F equals ma becomes 1/2 mv squared. So says you. Says you, momentum becomes some complex 1/2 mv squared thing. No, it doesn't. No, mv does not become, I'll throw a half in front of it and I'll square the end of it. None of that has anything to do with momentum. All right. And it has nothing to do with the invention of this 1/2 mv squared. Like, this isn't how the theory was invented. So it has nothing to do with the real history. All right, anyway, let's dig down a little bit to see if why it's tricky. Yeah, why it's contrived, how it's contrived. The first contrivance is changing F equals change in momentum over change in time, and changing that into whatever F equals m times this magical new world called acceleration. And acceleration is now just velocity over time, right? So they're playing the game again. It's in units per some measure of time. It's not total velocity. Okay. Force equals mass times acceleration. But in the other formula, so acceleration just has to do with a constant force again. You can't talk about acceleration if you don't have a constant force. If you don't have a constant force, you have an integral that could never be done, because the change in the amount of acceleration, can be almost infinitely diverse, and you wouldn't be able to solve for it. Anyway, so it's only in things like gravity where they can get away with this shortcut. Okay, let's dig down. All right. But the other formula we have momentum being, All right. Force equals mass times acceleration. But in the other formula, we have momentum being, so obviously it's not momentum, 1/2 mv squared. Well, that's obviously not momentum. So that is mass times velocity. Velocity and acceleration are not the same thing. Yeah, obviously they're not. But in the sense of when you're accelerating, they're exactly the same thing. During your acceleration, your velocity is is the byproduct of your acceleration. So it's pretty hard to say, well, what rate? Acceleration is a rate, and velocity is an amount. So that's the distinction. You want to talk about the rate of change. I want to talk about the total change, the volume of change. That's the difference. And so you're using math focused on finding a rate. I'm using math focused on finding a total volume. All right, anyway. Requires the force proportional to the mass, while the velocity doesn't. Okay. Acceleration requires a force proportional to the mass. Sorry, it doesn't. That's not what impulse is. It's not a constant force that hits something based on how heavy it is. No, it's a force, a constant. It's a total amount of force, and the only thing that's the limiting factor is that the velocity can only be passed on based on how fast something's going. I can't push a car 60 miles an hour, but I can push one 22, let's say, miles an hour. Okay, I can do that. You're my maximum speed. I might be able to push a car, but I can't do 60. Just because I can't push it. Okay, I can't give it higher velocities than I can move, because as soon as I give it a velocity faster than my own velocity, it's leaving. I can't even push on it anymore. It's too silly. Well, anyway, I was not, you just have a view of what energy is that just, I don't understand how it has any physicality at all. How do you physically understand what energy is if you don't understand that it's based on taking a particle and moving it? And if I double its mass, okay, and I give it the same force, it has to move less because I've spread the velocity over twice as much mass. How can you not understand that? Anyway, if you have a velocity, you don't need to keep adding to that velocity. If you do, you end up with an acceleration. So again, exactly the point, that this is totally unapplicable to impulse collisions, which don't have anything to do with necessarily acceleration. Now, a spring, we don't get to see. See, I mean, it'd be nice if there were a really good slow motion of a spring expanding, where we could just measure how fast the object's moving and how fast it gets to its maximum speed. That would be very interesting for the sake of these conversations. But we don't have that. But I'm just saying, in a lot of cases, the impulse isn't going to be over some huge amount of time. It's going to be happening almost instantaneously, and the explosion is going to happen, and the little bits are going to be moving, half the speed of light. Some of them are going to be moving actually the speed of light, right? The photons are actually going to hit something like after an explosion and give it an impulse. And then other pieces of energy moving different velocities are going to hit it and give it an impulse. So, it's not going to be some constant force. There's not going to be anything constant about it at all. Just like, say, you getting hit by the shock wave from a nuclear bomb. First, the light hits you, right? And then other pieces of radiation hit you, the gamma, beta, whatever's, the stuff moving almost the speed of light stuff. And then you'll get hit with the air, the air that got pushed. And, then you'll finally start getting hit by bits and pieces of sand and dust and, microparticles, little pieces of people, ground, burned, it's incinerated, little bits of carbon. So it's, what are you going to say? You're going to calculate it with this bogus formula, the energy transfer? Because there's no constant force. There's a bunch of little elements of force moving all kinds of different velocities that are going to decide your total velocity. The total force that changed your momentum. How do you understand this as some other theory than that actually being the process? Things with momentum hit you, and you either acquire their momentum or you reflect some portion of it or something like that. You either absorb the momentum or you reject the momentum. How can you understand is anything else happening? I just don't understand that. I'm sorry, this has always been like the photon crap. I never had any. I didn't even really know, frankly, until until the physics girl video. Really, I didn't really know kinetic energy meant this wacky formula. Like, I had seen the wacky formula before, but I didn't think the wacky formula. I just thought of it as some kind of bullshit. I didn't think anybody thought that was actually energy. I thought that was some energy for some specific purpose. I didn't think that's what you were saying. Everything has this kinetic energy formula bullshit in it. It's always been a momentum universe for me. All right. It's just so strange. So we are not saying the same thing in those two different formulas. Okay, so if you don't have velocity, you don't need to keep adding to that velocity. If you have a velocity, you don't need to keep adding to that velocity. I don't know what that could mean. If you do, you end up with an acceleration. Yeah. When your velocity is changing, that's called acceleration. Now, even though the change could be negative and it's really deceleration, but anyway, so we are not saying the same thing in those two different formulas. So again, this is just such nonsense. The formulas are describing the amount of weight, pressure, power, workability, joules. It's describing exactly what it's capable of. What can it transfer? What does it have? What's its volume? Again, it's a clear volume, Momentum creates a volume. You're saying the volume is this exaggeratedly, preposterously big thing because you multiply the volume times the number of velocities. You create this extra energy. So the more velocity you have, you just keep, increasing by the square, the amount of velocity, and make your energy bigger and bigger and bigger and bigger, even though there's no reason to believe you got more free jelly, that you're getting more to spread over your mass. But the answer has to be the same, or we end up with horrible mistakes when we apply them in reality. So again, it's just silly. The answers have to be the same. They're not the same. They can't be made to be the same. mv does not equal 1/2 mv squared. You can keep saying it does, but it doesn't. They're two different answers to the same question. All right, acceleration after a time reaches a certain velocity. So as I just pointed out, this is just gobbledygook, right? Because we're not talking about, none of these events are likely have anything to do with constant forces. The application of the pressure is not constant. It's not 10 pounds, 10 pounds, 10 pounds, 10 pounds, 10 pounds. No, it's 10 pounds, 9 pounds, 8 pounds, 7 pounds, 6 pounds. Okay, so we put in an acceleration which is time and force dependent. No, which is obliged to be in units and created into a rate. Even though it can't be put into a rate because it's changing from 10 to 9 to 8 to 7 to 6. So it's not a constant rate. Okay, and we want to find out how much momentum the object now has, which is mass times velocity. But if we do it like that, we end up with a nonsense answer. So you say it's nonsense. I say you haven't demonstrated, and you can't point to any experiment where you can say, see, Newton's mechanics don't work. Newton was full of shit. He didn't know what energy was. If you just use momentum and call it energy, what's the problem? What scenario do you get wrong? Now, I would argue you get lots of them wrong because you think a tiny little asteroid going really, really fast has a preposterous amount of energy, and it doesn't. Okay, I think you made a simple mistake. I think you made a lot of stupid mistakes where, what do you even mean, a velocity times a velocity? How does it make any sense to you to square a velocity? Why would that geometrically work in the universe? How does that make sense to creating something that would be relevant to creating a fuel? Squaring the velocity. Momentum makes so much more sense. I just don't know how you could have said momentum sucks. What made you say that? What made you say, oh, momentum sucks? What shitty answers? We need to find something better. I mean, where did you think about like the car and say, oh, it's obvious. If I remove half the mass from the car, I'm only going to gain 0.4. Yeah, I'm not going to gain much, I'm only going to gain this much. I'm not going to gain this much. And we're just going to gain this much more velocity. So why bother? I mean, what made you think that way? Okay, one we all are prone to doing by thinking of acceleration and velocity as the same thing. I've never thought of acceleration and velocity as the same thing. It's never been a problem. I've always known that acceleration is a bullshit term, frankly. It's describing change. How could it ever be something when it's describing a moment? Every single moment your acceleration is changing. Even in gravity, it's the fucking truth, and you people won't even admit it. In the first meter, you're supposed to be going 9.8 meters per second. Well, you're obviously not doing that because you only travel 4.9 meters. I mean, your acceleration rate is only 4.9. You don't accomplish the task of achieving the frickin' acceleration you're supposed to be accelerating out. You don't get the right distance. Right, so if it was 10 meters, you're only going 4.9. You're supposed to get 10 meters in 1 second, and you only get well, 9.8, and you only get 4.9. So you're clearly not going what it says the rate of your acceleration is. You're clearly not accelerating at that rate, or you would have gone the right amount of time. I mean, in the right amount of distance. So but the fact that you didn't make the distance means your acceleration rate, your actual velocity through that period of time was not 9.8. Yeah, well, whatever. By thinking of acceleration and velocity as the same thing, but they are different. Acceleration has to lead to a velocity. And I'm arguing clearly that the rate at which you are accelerated in impacts is never constant. No car crash is there a constant rate of deceleration or a constant rate of acceleration. Okay. So it's just mush. I thought there was a reply to that. Oh, here it is. He's looking for the theory that says it's okay to destroy conservation of momentum. If such a theory exists. Yes, it has to do that, and it has to explain the paradoxes. It has to explain, well, why don't I just keep replacing light things with heavy things and make free energy? Free momentum. Free momentum has to be understood to be free energy. I don't think you people could deny that. That if I'm making momentum, if I'm giving something more momentum, I have to be giving it more energy. It just can't avoid that. All right. So we'll just stick to that subject and leave it there. So this is not satisfactory. This is not going to resolve the dispute, obviously. This little gibberish about little math tricks. And they're not even that creative again. It's the square root of 2 for everything that has a 2-to-1 ratio. So any set of numbers that create a 2-to-1 ratio, that's the square root of 2. Okay? And they claim it happens, but they have no theory, no evidence of their theory being real, except for Stephen Bro's experiment, right? Brough. And again, as I pointed out, the trick with springs is you can't have them attached to the lighter object. If you attach the spring to the lighter object, you will degrade some portion of the energy of the spring because you're actually stretching the spring. You're actually helping it expand by tying it to a moving object. All right. So, till the next time and such, so forth and whatnot. Yeah, that's enough. I think that's enough. Yeah, that's enough. All right. So, this, like I said, this whole thing is just going to have to progress. We're going to have to get through all this crap, and there really is going to be a point where we're going to know better. Because none of it can exist the way it is. The answers so far suck. They don't resolve anything. They don't solve this. It's completely unsolved. There's no mechanics. There's no way of fixing the paradoxes. Again, you have to commit to saying that energy really is kinetic energy and momentum is a lie. Or you have to commit to momentum is the truth and kinetic energy is bullshit. If you force them both to be something, they're always going to paradoxically force you to break fundamental laws. You have to kill momentum as an idea to believe in kinetic energy. And if I'm going to be forced to concede kinetic energy as some kind of real thing, and I conserve momentum, I have to break any reality to kinetic energy. And that's just the simple truth. Kinetic energy is that's the broken bit. The bit we never needed. There was nothing wrong with Newton's mechanics. This new mechanic didn't need to show up. This new theory didn't need to arrive. It didn't solve problems Newton didn't already solve. And the only why it was moved forward is through bogus ferrocell Ken Wheeler shenanigans. Crappy experiments that didn't that provided a wrong intuition, that deceived people. Clay experiments, for example. They were just deceptive. Fact. And if it wasn't for those stupid experiments, this theory wouldn't exist, and you'd all be perfectly happy understanding that everything's made out of momentum. It's just the truth. It would be nothing. There's no place you can point where, oh no, without kinetic energy theory, the universe breaks. No, there's no such place. All right. So anyway, whatever. I can only do my half of this. I can only try to make reasoned arguments and, get you to understand why this is a mush answer. This is not solving the paradox. This is not a sensible. To say these two theories are compatible when they give different answers to the same question is just so overtly in denial. I mean, it's a denial of logic to say such a thing. It's just overtly saying you just don't care about mechanical physics making any sense at all. 2 equals 7. That's what you're saying. You know it in your heart. Everybody should believe 2 equals 7. That's how different the numbers are. Kinetic energy says 7. Momentum says 2. They're not equal. They're not the same thing. They're not compatible. They're in overt conflict. Alright, so anyway, this has been a DraftPhysics.com video presentation. I can only reason with you people.